Deep inside the Gobi Desert, hidden from satellites, and tucked away near the Mongolian border, there is a building most people on Earth have never heard of. Inside that building is an experimental nuclear reactor that, until recently, the world considered impossible. It runs on a substance the United States military first tried to use in 1946, then abandoned by 1954. It cannot melt down. It produces 200 times less waste than conventional nuclear plants. And in April 2025, Chinese scientists did something with it that no one had ever done before in human history. The reaction they sustained inside that desert facility may not just transform China's energy future. It could quietly mark the end of the oil-based economy that has dominated the world for over a century. To understand why this matters, you need to understand how dependent the modern world really is on oil. Every year, humans extract approximately 100 million barrels of crude oil from the earth. That oil fuels cars, ships, aircraft, and power plants. It produces plastics, fertilizers, asphalt, and thousands of industrial chemicals. The entire global economy, valued at over $100 trillion, depends on the steady flow of oil from a handful of producing nations. But oil has three fundamental problems. First, it is finite. Most reliable estimates suggest the world has between 40 and 50 years of recoverable reserves at current consumption rates. Second, it is geographically concentrated. The Middle East, Russia, the United States, and a few other countries control most production. Geopolitical tensions over oil routes have triggered wars, sanctions, and political crises for the past 75 years. Third, burning oil releases massive amounts of carbon dioxide. The energy sector is responsible for over 75% of human greenhouse gas emissions. Every government, every think tank, every research university on the planet has been searching for an alternative. And China, under the radar of most Western media, has been quietly running an experiment that could change everything. The facility is officially called the Thorium Molten Salt Reactor, or TMSR. It was built by the Shanghai Institute of Applied Physics under the Chinese Academy of Sciences. The location was chosen carefully, a remote site in the Gobi Desert, away from population centers, with stable geology and minimal seismic activity. Construction began in 2018. The reactor went critical for the first time in October 2023. Then in June 2024, it began generating power. It produces just 2 megawatts of electricity, which sounds small compared to standard commercial reactors that generate over 1,000 megawatts. But 2 megawatts is enough to power roughly 2,000 households. And more importantly, it is the first working thorium molten salt reactor anywhere in the world. The reactor is small enough to fit inside a shipping container. It does not use solid fuel rods. It does not need massive cooling towers. It does not require huge water supplies, and it is fundamentally incapable of melting down. To understand why this matters, you have to look at what makes thorium reactors different from everything that has come before. Conventional nuclear reactors use solid fuel rods made of enriched uranium. The fuel sits inside the reactor core, where neutrons split uranium atoms in a process called fission. This releases enormous amounts of heat, which boils water into steam, which drives turbines, which generate electricity. The problem is that conventional reactors can fail catastrophically. If the cooling system stops working, the fuel rods overheat, they can melt through their containment. Steam pressure can cause explosions. Radioactive material can be released into the environment. This is exactly what happened at 3 Mile Island, Chernobyl, and Fukushima. Thorium molten salt reactors work completely differently. Instead of solid fuel rods, they use liquid fuel. Thorium is dissolved into a molten salt mixture that flows continuously through the reactor at temperatures above 600 degrees Celsius. When the reactor heats up, the fuel salt actually expands and spreads out, which automatically slows down the nuclear reaction. If something goes wrong, a plug at the bottom of the reactor melts. The liquid fuel drains into a holding tank below ground, spreads out, cools, and solidifies. The reaction stops on its own. No human intervention required. No explosion possible. No meltdown possible by physics. Now here is the strangest part of this story. China did not invent thorium reactor technology. The United States did. In 1946, the U.S. Army Air Forces, the predecessor to the modern Air Force, began researching molten salt reactors as part of a project to build a nuclear-powered supersonic aircraft. The research was conducted at Oak Ridge National Laboratory in Tennessee. Scientists there built the world's first operational molten salt reactor in 1965. It ran successfully for 4 years. The technology worked. But by the early 1970s, the United States government made a strategic decision to focus on uranium-based reactors instead. Several reasons drove this choice. Uranium reactors produced plutonium as a byproduct, which was needed for nuclear weapons during the Cold War. Thorium reactors did not. Uranium-based research had a stronger industrial infrastructure already built. Switching paths would have been expensive, and so by 1976, the Oak Ridge thorium program was officially closed. The research was published openly, the scientists moved on, and the technology sat dormant for nearly 5 decades. Then in 2011, the Chinese Academy of Sciences launched a national initiative to develop thorium reactors using the abandoned American research as a starting point. The man chosen to lead the program was Jiang Mianheng, son of former Chinese President Jiang Zemin. He hired thousands of researchers. The project was funded with over $3 billion, and in 2025, that investment produced results no one anticipated. On April 8, 2025, at a meeting at the Chinese Academy of Sciences in Beijing, the lead scientist of the project, Professor Xu Hongjie, announced something that had never been done before. The team had successfully refueled the Gobi Desert reactor while it was still running. To understand why this is significant, you need to know what refueling a conventional nuclear reactor involves. Standard reactors must be shut down for weeks at a time to replace their fuel rods. This is a major operational disadvantage. It means scheduled downtime, lost power generation, and complex safety procedures every time refueling happens. Liquid fuel reactors, in theory, should be able to be refueled continuously without shutting down. But until April 2025, no one had ever demonstrated this in a working reactor. The Chinese team achieved it. They added fresh thorium fuel salt while the reactor continued generating electricity. According to the Chinese Academy of Sciences press release, the operation lasted several hours and went exactly as planned. Professor Xu told assembled scientists that this proved the design works in the real world, not just on paper. The implications are massive. A reactor that never needs to shut down for refueling could potentially run continuously for decades. The economics of nuclear power would change completely. Then, in 2025, another piece of the puzzle was revealed. China's Ministry of Natural Resources announced the results of a comprehensive national geological survey. The findings were extraordinary. China possesses, according to current estimates, enough domestic thorium reserves to meet its entire national energy needs for approximately 60,000 years. That is not a typo. 60,000 years. To put that number in perspective, all of recorded human civilization is roughly 10,000 years old. China now possesses enough fuel for a fully functioning industrial civilization 6 times longer than human history has existed so far. The thorium is concentrated in Inner Mongolia, in tailings from existing rare earth mining operations. This means China can extract it as a byproduct of mining it is already doing. The cost of extraction is minimal. The supply is essentially limitless. Meanwhile, the United States has substantial thorium deposits in Idaho and Idaho and several western states, but no infrastructure to use them. The European Union has small reserves but limited research programs. India has the world's 3rd largest thorium reserves and has been trying to develop thorium reactors since the 1950s, but progress has been slow. Right now, China is alone in possessing both the resource and the working technology to use it. The 2-megawatt test reactor in the Gobi Desert was never meant to be a commercial power plant. It was always intended as a proof of concept. With the April 2025 breakthrough complete, China is now moving rapidly to scale up the technology. A larger 10-megawatt demonstration reactor is currently under construction at the same Gobi facility, scheduled to come online by 2029. This larger reactor will test commercial-grade operations, including refueling cycles, waste handling, and long-duration power output. Beyond that, a 100-megawatt thorium reactor is being designed for deployment by 2035. This would be approximately the size of a small commercial power plant. By the late 2030s, Chinese energy officials estimate that thorium reactors could provide between 10 and 20% of China's total electricity generation. Beyond electricity, there are additional applications being researched. Thorium reactors can produce process heat at temperatures above 700 degrees Celsius, which can be used for industrial hydrogen production, desalination, and synthetic fuel manufacturing. The Chinese Academy of Sciences has also begun research on portable thorium reactors small enough to be deployed in ships, military bases, and even on container vessels. If these applications materialize, the implications go beyond electricity generation. They could begin replacing oil-based fuels across multiple sectors of the economy. Thorium is not the only energy breakthrough happening in China right now. Approximately 1,800 kilometers east of the Gobi reactor in Hefei in Anhui province sits another facility that has been making global news. It is called the Experimental Advanced Superconducting Tokamak, or EAST. International media often refers to it as China's artificial sun. On January 20th, 2025, the EAST reactor maintained a stable plasma reaction at over 100 million degrees Celsius for 1,066 seconds. That is more than 17 minutes of continuous nuclear fusion. The previous world record, set by EAST itself in 2023, was 403 seconds. The Chinese team more than doubled it. In January 2026, EAST broke another barrier. It successfully maintained plasma at densities previously considered impossible, a major step toward practical fusion power. Then, in November 2025, the Chinese Academy of Sciences and European partners jointly launched a major new program called BEST, the Burning Plasma Experimental Superconducting Tokamak. The goal is commercial fusion power by the 2040s. China is also building a separate facility in Nanchang called the z-ffr, the Z-pinch-driven fusion fission reactor. This is a hybrid design that combines fusion and fission to generate 100 megawatts of continuous electricity for the national grid by 2030. Estimated cost, $2.76 billion. Construction began in early 2025. China is currently the only nation pursuing this specific design at this scale. Now let's discuss what this all means in practical terms. Together, China's thorium reactors and fusion projects represent the most coordinated energy transformation program in the world today. The Chinese government invests approximately $1.5 billion per year in fusion research alone, which is roughly double the US government's annual investment in the same field. Private Chinese investment adds billions more. According to Nature and Financial Times reporting, total global private investment in fusion energy reached $10.6 billion between 2021 and 2025. China captured a significant share of that funding. Beyond the technology itself, China has built the supporting industrial base. Over 80% of the world's solar panels are manufactured in China. China produces 60% of global wind turbines. China dominates rare earth refining, lithium battery production, and high-voltage power transmission equipment. When you combine working thorium reactors, leading fusion research, manufacturing dominance in renewables, and 60,000 years of domestic energy reserves, the picture becomes clear. China is building an energy system that can operate independently of global oil markets, free from Middle Eastern supply disruptions, and largely outside Western financial control. The United States, by contrast, is still primarily dependent on a mix of oil, natural gas, and conventional nuclear power. Its renewable energy build-out has been slower than China's. Its fusion research is well funded by private companies like Commonwealth Fusion Systems, but lacks the coordinated national strategy that China brings to the table. Looking ahead, the timeline is aggressive but credible. By 2029, China expects the 10-megawatt thorium reactor to be operational. By 2030, the z-ffr fusion-fission hybrid is targeted to begin feeding electricity into the grid. By 2035, the first commercial-scale 100-megawatt thorium plant is planned. By 2040, China aims to have a demonstration fusion reactor producing meaningful power. And by 2060, China has committed to carbon neutrality, with thorium and fusion expected to play major roles. None of this guarantees that oil will actually be replaced. The global economy is enormous, and the existing fossil fuel infrastructure has trillions of dollars invested in it. Transitions of this scale take decades, but the technological foundation is being laid right now, in real time, in laboratories and reactor sites scattered across China. And it is being done while most of the Western world is still arguing about whether such transitions are even possible. The phrase "replaced oil forever" is provocative. The reality is more nuanced. Oil will not disappear overnight, but the era of oil as the unquestioned dominant energy source for industrial civilization may be entering its final decades. And the nation building the alternative is not the United States. It is China. If this video gave you a clearer picture of what is actually happening in the global energy transition right now, hit subscribe to follow more deep dives into the technologies reshaping our world.